We specialize and focus on terahertz radiation, so very far infrared, low frequency radiation, generation, detection, and applications. We are trying to develop new detector methods or new detector types for the terahertz radiation, which typically has been a very complicated matter due to the fact that the terahertz radiation is at such low frequency and low energy that existing technologies known from visual light or from infrared frequencies are not applicable. So what we have here is one of our prototype terahertz photomultiplier tubes. We have developed these in collaboration with our partners in Japan, Hamamatsu Photonics. And much like a conventional photomultiplier tube, we would take where visual light or infrared light photons would interact with a medium to free up an electron, and this electron is then multiplied in this cascade of diodes, shown here as a gold metallic structure, then leading to a signal. With the terahertz photomultiplier tube, we circumvent the problem that the photon energy of the terahertz photons is far too low to drive any photo effect. And instead, what we do is we shine the light onto a metasurface, and this metasurface enhances the electric field of the terahertz light wave, and the electric field in turn leads to quantum tunneling. So the hard piece of our terahertz photomultiplier tubes are, as mentioned, relying on the quantum tunneling effect and not on the photoelectric effect. For this, we have designed special resonant structures on a microscopic scale, which we term the metasurface. What we see here is a larger 4-inch wafer where we have 52 such metasurfaces. And in each metasurfaces, what happens is that the incoming electric field of the terahertz light wave will be concentrated and enhanced at very small specific tips, a few nanometers wide, where the electron tunneling process then occurs. Due to this principle of the electron emission being dependent on the terahertz electric field, we now have a field-sensitive detector, which is different to established technologies which typically rely on some accumulated heat. And one core advantage of this is that the field has a directionality, the polarization and the polarity of the electric field. When measuring heat-sensitive detectors, this information is lost. However, with our detectors, due to special asymmetries in our structures, we are able to determine the absolute polarity of the terahertz incoming electric field, as well as its polarization. Once the electron has been liberated, it cascades through this set of diodes, as mentioned earlier, and leads to a detectable current or voltage, which is then depicted on an oscilloscope. This way, we have a direct feedback, which is dependent on the incoming electric field. In terms of applications, there are two more principles of this technology that are highly important. Point one, it is scalable to any frequency within the visual or infrared to the terahertz or microwave wavelengths. So there's a broad tunability of this detector. Point two, the reaction or the detection signal has a strongly nonlinear reaction or behavior connected to the incoming quantity of the electric field. This leads to one of the main application ideas that we have for this detector, being that it can sense very small changes which affect the terahertz electric field on a minuscule scale, but will therefore yield a very strong difference in signal. So whereas a small change with a linear detector, such as a heat-based detector, will maybe not show any difference with a tiny change, our detector can definitely see this change due to its strong nonlinearity. In real-life applications, this would be very useful for spectroscopy, where one wants to sense perhaps tiny traces of some gas. May it be a poison, may it be a leak in some underwater reservoir. Many applications in chemistry and drug detection. Another application would be in the semiconductor industry, where we could possibly revolutionize the precision on how the doping is controlled within any sort of wafer, silicon-based, germanium-based wafers. Due to this mentioned nonlinearity, we can get a very, very strong response from a very minuscule change. And going down the same path, this can also be used for monitoring the homogeneity of certain surfaces, for example, graphene over a large area, or any other material where we can get some sort of reaction from the terahertz light bulb as it interacts with these materials and then goes back to the detector. We are offering A new detector with a very fast response time, simple operation that works at any frequency desired, in a range that is not accessible for classic detectors that are relying on a photoelectric effect.